שלום ואחרי צהריים טובים לכולם, וכמובן אוטוטו פורים שמח לכולם. ברוכים הבאים לוובינר של BrainChip ו-Eastronics בנושא פיתוח אופטימלי של מערכות קצה המשלבות יכולות בינה מלאכותית בעזרת מעבד ניורומורפי של חברת BrainChip. שמי אוזן אבנר ואני מוביל את הפעילות של בינה מלאכותית ב-Eastronics. שילוב טכנולוגיות של בינה מלאכותית בפיתוח מערכות בכלל ובמערכות קצה בפרט במקום שבו המידע נוצר תופס תאוצה בשנים האחרונות. כמעט כל חברה, ולא משנה לאיזה פלח שוק היא מכוונת או שייכת, נמצאת בשלב של בחינת הטכנולוגיה לצרכים שלה, או הטמעה של הטכנולוגיה בפתרונות שהיא מפתחת. במקביל, אנחנו גם עדים ליותר ויותר חברות בעולם, וגם בישראל, המפתחות מעבדים ייעודיים לטובת מימוש אלגוריתמיקה של למידת מכונה ולמידה עמוקה. מעבדים אלו מפגינים, לאחר תכנות מתאים כמובן, רמה מסוימת של התנהגות אנושית במכלול משימות קוגניטיביות ובפתרון בעיות. הוובינר היום מתמקד בפתרון של חברת BrainChip, המציעה מעבד ייחודי למימוש אלגוריתמיקה של בינה מלאכותית, ליישומי קצה דלי הספק במיוחד. משתתפים איתנו היום בוובינר אורחים מחברת BrainChip. מכיוון שחלק מהם יושבים בקליפורניה שבארצות הברית, ועל מנת לחסוך להם השכמה בשעה מאוד מוקדמת, החלטנו להקליט מראש את המצגת שלו. בנוסף, יש איתנו אורח מהמשרד של BrainChip בצרפת, שיקח חלק פעיל בהשתתפות בוובינר הזה. אני רוצה ברשותכם לעבור לאנגלית, לטובת האורח, והמשתתפים שאינם דוברי אנגלית. So again, good afternoon to you all, and welcome to BrainChip and Eastronics webinar on the topic of developing optimized edge system with BrainChip's Akida Neuromorphic processor. My name is Avner Uzan, and I lead the AI acceleration activity at Eastronics. And I will be your moderator, and I will be the moderator and the host for the webinar today. Our guests and presenters are Mr. Rob Telson, Vice President of Worldwide Sales at BrainChip United States. Mr. Todd Vieira, Director of Customer Engagement at BrainChip United States. And Mr. Gilles Bézard, Field Application Engineer at BrainChip France. Agenda is the following. Although some of you are familiar with Eastronics, I would like to spend a few minutes to introduce you with our activity, mainly in the embedded systems arena. I will then hand over to Rob and Todd to conduct the main session for today. We also plan to have a demonstration of BrainChip technology with detailed explanation. This demo will be conducted by Gilles Bézard. We reserve some time to go through a Q&A session, and our plan is to conclude this webinar at 3 p.m. Israel time. For those who are not familiar with the Zoom platform, please be aware that you can submit questions via the Q&A icon in the bottom of the Zoom application window, as you can see currently in my slide. So a few words about Eastronics and our activity within embedded system and specifically in the area of artificial intelligence. We have several activities or business units, if you will, within the embedded systems group. Each business unit has a different technological focus and, of course, different vendor solutions that we promote and distribute in Israel. For example, embedded systems department on the left side. This department provides boards and complete systems solutions from vendors like Intel, Advantech, Control, and others. All business units except artificial intelligence have a strong presence in a variety of projects in the Israeli high-tech industry. The artificial intelligence business unit is pretty much new in our activity. But what does it mean, AI activity in Eastronics? Because of our core competence, experience, and accumulated knowledge in the field of hardware, components, and systems, it seems very natural to us to focus on the hardware side of AI technology. Our mission, or vision, if you wish, is to provide hardware-based, innovative, and state-of-the-art AI acceleration solutions for a wide variety and range of applications. We established half a year ago a formal partnership with BrainChip, and we are working together to share the vision and promote the Akida technology in the region. We'll hear more about this today. We are also in touch with other vendors that provide hardware-based AI acceleration solutions that are complementary to the technology that BrainChip is offering. Let's now move to the main session for today. I will hand over to Todd and Rob to conduct this session.
Thank you, Avner, and good afternoon to all of you, and thank you for attending our online seminar today. My name is Rob Telson, and I'm the Worldwide Vice President of Sales at BrainChip. And with me today is my colleague, Todd Vieira. Todd is our Director of Customer Engagements at BrainChip. We at BrainChip are aware of the extensive research and development activity in the high-tech market in Israel, as well as the great innovation that this market is leading. We also believe that BrainChip's innovative technology can bring significant value to these activities. BrainChip operates in Israel through our business partner, Eastronics, which is the representative and distributor of BrainChip in this region. I'd also like to thank Eastronics for organizing and setting up this event. We truly appreciate your time. Look forward to educating you on Akida, our neuromorphic neural net processor. And we also look forward to any questions that you have during this event or after. So just to tell you a little bit about BrainChip, we were founded in 2013. We have over 15 years of AI architecture research and development experience, specifically focused on the neuromorphic architecture and how it functions within the brain. We have almost 70 employees. Most of them are data scientists, hardware and software engineers. And our goal right now is to be over 100 employees by the end of the year. We have 21 patents, patent pending included, on our technology. We're publicly traded on the Australian Stock Exchange and in the US on the OTCX. Our whole focus is about edge AI devices. And when we speak of edge AI devices, we believe that the edge AI devices, it spans the range from wearables, such as watches, all the way up to electric vehicles or unmanned vehicles. Anything where the power envelope is important, and incorporating sensors in order to make these technologies and these devices smart. So we focus on making sensors smart. And we do that by driving our AI technology through 5 sensor modalities, such as audio, gustatory, olfactory, tactile, and vision. And we'll talk about that in more detail. Our North America headquarters is in Laguna Hills, California, right next to Laguna Beach. We also have an engineering center in Toulouse, France, a development center in Hyderabad, India, and our advanced research center in Western Australia. So as I mentioned before, when we think about edge AI computing, conventional AI captures data from sensors and it sends it to the cloud for processing. Large data sets, high bandwidth, computationally inefficient, and power intensive. And that's how AI operates today. It consumes a lot of everything. But when we think about AI at the edge and on devices at the edge, and utilizing BrainChip's Akida processor, it brings intelligence to the sensor in the device. And we can do that with computing on the chip. An order of magnitude less data in computation. A fractional of power enables one-shot learning for device personalization And we're doing all of this without depending on communicating with the cloud, which leads to another level of privacy and security. The Edge AI device market outlook as of today, by 2025, they believe the TAM for Edge AI devices requiring AI is roughly about $60 billion. And what does that mean as it continues to grow dramatically? Is that there's going to be this demand for more capability, demand for more data, the demand for more compute, and the demand for more bandwidth. So traditional AI is going to be challenged, and it's going to have struggles trying to support this demand as everything moves over to the edge. So really, as current AI compute architecture is unsustainable, and we need to move AI to the edge, that's where we need to solve our problems, and that's what BrainChip's doing. A perfect example, when you look at AI today at the edge, most companies are presenting some type of solution that does this: bounding boxes around objects, in this case vehicles, and people, and highlighting the level of accuracy. BrainChip looks at AI in a completely different perspective. Here, we're going to demonstrate an in-cabin solution for a vehicle, but this also could represent solutions for the home or in the industrial application environment as well. And we're running 3 different networks, one recognizing faces, one recognizing keywords, and one recognizing when someone is in the screen, such as visual wake. And as you can see here,
Hey, Akida.
Aaron, all systems active.
Hey, Akida.
Todd, all systems active.
we're making the in-cabin vehicle experience much more efficient, much more effective, with personalization and consuming very little power with our device, focusing on these 3 functions, with facial recognition consuming 22.6 milliwatts, and visual wake, recognizing that someone's in the screen or in the frame, consuming 6 milliwatts, and voice recognition consuming 600 microwatts. And again, we see this type of device personalization in edge devices from the vehicle all the way to applications in the home. Why does this happen and how do we do it? Well, our neuromorphic architecture is what makes us unique, and there's 4 key design principles. The first one being distributed computation. See, computation spread across many cores or neural processing units that we call NPUs. And each NPU has its own dedicated computational engine and memory, which reduces the data movement. The second is event-based processing. And this is key because non-zero activation map values are represented as multi-bit 1 to 4-bit events. And NPUs only perform computation on events, not on activation maps. This is really important because traditional AI today has to focus on non-events and events in order to provide their solution. By not having to focus on non-events, we're reducing 50% of the compute effort and immediately reducing the amount of power consumption as well. The third is event-based communication. NPUs that communicate by sending events to each other over a mesh network without host CPU intervention. The neural network connectivity is configurable in the field. This is also very important because a lot of the compute that we do, if not all, can be done on our device. And lastly, the event-based learning. A key differentiator for Akida and what BrainChip is offering, Akida implements an on-chip learning algorithm with no costly communication to the cloud, which enables you to have this level of flexibility and programmability on your device without having to retrain it include new network development, or have machine learning guys involved. So Todd, if you could please take over from here, I'd really appreciate it.
No problem, Rob. I'm going to talk a little bit about AKD 1000. And this is the reference design BrainChip has developed so that you could get access to our technology in a reference design development kit of your choice. Now, if you look at the top part of the screen, it's all the data inputs you can take to bring in your sensor data, USB or PCI Express for images such as CMOS imaging, LiDAR, radar, etc. I2S, I3C for audio or vibration analysis. We have an LPDDR in order to have extra weights and activations if you want to have that off chip. And then we also have the neuron fabric, which is the key to our IP development technology inside AKD 1000. Inside our neuron fabric, we have 20 nodes, and each one of those 20 nodes has its own MPU, as Rob talked about on the previous screen. And each MPU will do its own compute and pass that information to the next MPU. And we have various different low power states. So now I can actually run any one of your AI algorithms at various different options so I can reduce the power when any one of those MPUs are not in use. Next slide, Rob. And in developing your network, we have MetaTF. MetaTF stands for Meta, which is post, and TF, which is TensorFlow. As you can see in the light blue boxes, that's your traditional TensorFlow environment when you're developing the models and networks that are for your specific use case. And what we've done, we've added some API extensions that allow you to convert your current model over to an Akida proprietary model that allows you to run on any one of our Akida devices or Akida IP. So if you take a look at that training set that has in TensorFlow, normally you quantize down to either 32, 16, or 8 bits. And what we've done, we've added some extensions within the TensorFlow Keras environment to quantize down to 4 bits. Once we quantize down to 4 bits, that's going to reduce the memory you need in your design, further increasing the efficiency of Akida and your network. If you happen to lose any accuracy within that, we can bring back the quantize aware training in the next block called fine tuning, and that allows you, if needed, to rerun some of your epochs through your data set and bring back your accuracy to the original state. And from there, we convert it to an Akida model, and this will be able to run on the Akida hardware. So as you can see, this is our MetaTF development environment. If you go to brainchip.com/developer, you get access to the installation manuals, user guides, API reference, and some examples. And when you first start off, you do not even have to have a model or a network or a data set. You can use some of the homegrown custom models that we've already generated for you in your environment, and you can convert your, you can use those to run your CNNs. And then once you have your own data set, you can actually use some of the models to build your own custom data sets. And we're very excited about this. Over in 2021, we've had over 5,000 new users adding Akida meta development environment into our into their environment. And once you have your MetaTF development environment up and running, you can purchase some of the hardware that'll extract power numbers and necessary timing associated with the hardware that you're looking for. So let's take a look at AI processing on the edge. The key to Akida is running in the embedded application. You can run some image classification, face detection, keyword spotting. All these models are meant to be ran on the embedded environment. If you're doing some more complex models that needs a little bit of help from the host processor, we can also do that similar to the way traditional DLAs are working today. So what we try and do is spec out your environment to see what kind of constraints you have in your environment, optimize the model to work in that environment, and try and get as much of the network running solely on Akida to minimize your power and have really fast latency for your specification at the edge. And this takes a look at the sensor to inference. So as Rob has stated in the previous slides, we not only support vision, auditory, olfactory, gustation, and tactile sensors for vibration analysis. Any type of sensor data we can actually use in your traditional environment. And what we try and do is run a majority of those in standalone, or if they're more complex, we can actually run those with a host CPU. Next slide, Rob. So not only do we have a chip, the AKD 1000, but we also have various platforms to run a development environment on. We have the PC Shuttle, which is an Intel x86 based platform. We also has a Raspberry Pi development platform. And we also have Akida board standalone that can run in any one of your Linux type environments. We also have Akida IP. If you are designing a chip, you can integrate Akida IP into your chip for various different use cases, depending on the applications, the node, the foundry, and technology. It can be optimized to run in any one of your environments. So next, I'm going to show you edge-based learning. I think Rob's going to run through these demos. Go ahead, Rob.
Thanks, Todd. And so what we're going to do now is go through a set of demos for you. These demonstrations really highlight the differentiation of what we're doing at BrainChip. And so what I'm going to show you here is what we call edge-based learning. And this edge-based learning is we're basically learning new objects as we incorporate them into the data set, which we're not involved in any type of network or data set. And so here we're learning beer bottles. And we started with the Corona Premier beer bottle, and we added in capturing an image of a Rolling Rock. And now we're going to capture an image of a birch beer. And you'll notice it says one shot, which means we just captured a new shot or a new image. That's how easy it is. And now we're adding in a Corona Light, very similar to a Corona Premier. But what we're trying to do when it comes to Corona Light and Corona Premier is trick Akida and see how accurate it is. We bring back in Rolling Rock and it immediately recognizes it. Then we introduce birch beer and immediately recognizes it. The same is true for Corona Premier. Now let's bring in Corona Light. It has a little bit of a challenge focusing on Corona Light. So what do? We enter a second shot. This is how simple it is to provide another level of accuracy when it comes to adding a new image. So we do Corona Premier again. And now let's add in Corona Light. And Akida immediately recognizes it's Corona Light. This is a perfect example of a blurred vision. We focus and Akida recognizes it's Corona Premier. And this is a simple demonstration on edge-based learning. Now let's show you edge-based learning in a high-speed environment. And I hope this translates well over your internet speed. But what we're showing you here are 4 images that were captured. The first one being the pit crew, the second of the Formula One race car, the third of the motorcycle, and the fourth of the racetrack. This is an exciting demo. As we press play, you'll notice that Akida recognizes the pit crew, it recognizes the race car, and it recognizes the racetrack. Here comes the race car into frame. Running appropriately, you'll notice that the car moves in and out of frame quickly, blurry and bouncing. Nothing is still. The images are not still. Same with the motorcycle, which has the same color combination of the Formula One race car. Here comes the race car again. Akida immediately recognizes it's the race car. And again, in and out of the frames, blurry. Here comes the motorcycle, coming at a very high frame rate, moving fast through the frame and never still. And lastly, my favorite of them all is when the race car comes into frame at a very high speed, high rate, blurry and bouncy. And that's Akida in a high-speed performance environment.
Let me go here, Rob. You know, this is a very impressive demo for the fact that all this learning was taking place on the hardware itself. This was taken a standard model that we have on our website developers kit. You can download it in MetaTF. You can access our developers kit, create a demo such as this on hardware. There's nothing like it in the industry right now. I actually are creating shots on the fly, adding them to the hardware in a very efficient, fast pace.
Thanks, Todd. And even Robot Ken thinks it's great. So now let's move on to gesture control. And we see gesture being applied in a lot of different environments for device personalization in the home, device personalization in industrial applications, and device personalization in the vehicle or medical device applications. And what we're showing here on the left-hand side is, again, how easy it is to learn new gestures. And so what we'll do is we'll add in the gesture 1 using our one finger. We'll do the same and have it learn another gesture right here, and we'll add in number 2. And it learns that. On the right-hand side, I'm going to press play, and what you'll see is these are gestures which were already learned, and Akida is recognizing them quickly and accurately. We did right, left, and 1. When I move on to the next demonstration for gesture, what you'll see is, again, these are hand gestures that were already learned, and it's recognizing 1 here. But we're doing this using 3D point cloud, which is perfect example of a LiDAR environment and highlighting sparsity. And then the second one is the gesture 3. And again, Akida recognizes it's 3, but as he turns his hand, it looks like it might be 2, and it goes back from 3 to 2. And the last one will be gesture 5. And he highlights gesture 5. And again, another gesture classification demonstration. And we see this in different applications, as I mentioned before, from interior cabin in the vehicle to medical device applications to consumer and personal devices such as AR, VR headsets and gaming, as well as for personal devices in the home. Now let's look at something that everyone gets excited about. Let's talk a little bit about benchmark data. And when we look at the benchmark data, what we've done here is we're benchmarking our keyword spotting application, our AKD 1000, as Todd mentioned earlier, to Google Coral, NVIDIA Jetson, and an ARM N4. And this is based off the Google Speech Commands dataset. Todd, do you want to add anything before I move on to the next slide?
Sure. If you take a look at the DSCNN network that we ran on it, it was ran on all the designs to have a fair benchmark where everybody looked at everything the same way. So this is a traditional DSCNN, about 8 layers. Go ahead to the next slide, Rob. If you take a look at power, efficiency, and IBS for keyword spotting, most of the time, a lot of these designs out there are heavily over-designed. And over-design has very high IPS, but it has very high power as well. And a lot of these edge based devices that you're going to create out there, you have a power envelope that you're really trying to meet, and you don't want to heat it up as much as these devices do. So with Akida, we can actually be very flexible in how we run our network through our device. We have various different controllability in there to have it run. As you can see here, we're running at the max speed on the AKD 1000, which is 300 megahertz, and we get 99 milliwatts for 59 microjoules per inference. Or you can even run it in low power mode at 1 milliwatts, which is significantly more efficient than even a Cortex-M microcontroller at 37 microjoules per inference at 27 IPS. And the key thing is this is all scalable. It's scalable to foundry and process. So our technology is manufactured at TSMC 28 nanometers, but if you want to utilize our IP in lower and lower technologies, it'll scale down accordingly to those process and foundry specifications.
So all of this is what we get excited about. And here's a perfect example of one of our customers highlighting the success they've had using BrainChip's Akida. In this case, Mercedes-Benz, who launched their Vision EQXX vehicle during the Consumer Electronics Show in January, highlighted the fact by using BrainChip's Akida, they were seeing 5 to 10 times more efficient results than using conventional AI for voice control. And let's talk about an area where we are extremely excited, and this is vibration analysis and tactile sensing. And what we're going to demonstrate here in this first demo is tactile sensing. Basically, just think of the fact that we're taking a tablet and we're taking a stylus pen and we're hitting the tablet, creating digits. The digit on the right-hand side, for example, here is digit 0. The next digit is digit number 9. And what I'm going to do is pause this just to highlight running our CNNs converted into an SNN model using MetaTF. The power consumed to create the digit is 25.08 milliwatts. But if you wanted to use a native SNN model, you'd only be consuming 4.48 milliwatts, both extremely low in power. And this tactile sensing is the gateway to the development for vibration analysis. And what I'm going to show you in the next demonstration is true vibration analysis. And what we're doing here is we're going to turn on a fan. It's going to recognize the fan's working, and then we're going to stick something in the fan to create a defect or a conflict. And you're going to notice that Akida is going to recognize it immediately and highlight it. And this is an example of vibration analysis using our Akida Neuromorphic processor. And now let's have a little bit of fun. Although this is a fun demo, it actually addresses a lot of the environmental dynamics we're going to be experiencing in the future. And here we're going to focus on beer tasting. And thanks to Oscar's Brewing Company in Temecula, California, for loaning us the beer to use in this demonstration. But it's not about the beer, although that's fun. It's really about Akida and putting the sensor into the liquid and being able to recognize the alcohol content, the pH, the sodium, and the glucose. And consuming only 6.3 milliwatts of power, it's able to determine it's a pale ale. Now we'll give it a stout. And the same thing, as it goes through the process, it's able to determine that it's a stout, again, consuming very little power. It's not about the beer. It's about what we can do with the analysis. Maybe it be water predictability, the amount of chemicals in the water or other liquids. And it's just not about liquid compounds either. It could be about gases in the air or smoke detection or something to that extent. And that's when we get excited about Akida, because we're able to address all of these different senses as we highlighted before. So now we're at a point where it's the QA session, and we ask you, feel free to ask questions. Your questions are visible only to the webinar presenter. So at this time, your questions can be submitted via the QA icon. So please go to the QA icon and let's get some questions submitted. So in short, BrainChip. Traditional AI today is compute intensive, and traditional AI solutions do not address the future for edge AI environments. There's too much irrelevant data which is being processed, consuming too much power, and too many dollars are being spent in the wrong areas. The key is not to process more data faster, it's processing relevant data efficiently with accuracy. And neuromorphic computing, as highlighted during this demonstration, is the next generation of AI, processing the most relevant data, smarter, faster, and most economical. BrainChip, we are the first to market with a neuromorphic solution, and we're leading the way. So our mission is we don't make the sensors, but we make them very smart. We don't add complexity, we eliminate it. We don't waste time, we save it. And we solve the tough edge AI problems that others do not or cannot solve. So don't miss the bus. Take advantage of our one-shot learning, our localized processing, and our ultra-low power solutions. So intelligent AI everywhere is our mission. And again, thank you very much for attending our webinar today. And we are very much looking forward to engaging with you in this very advanced market in Israel and how we can help you with your next generation products. Thank you.
Thank you.
So thanks much to Rob and Todd for preparing and conducting this very interesting session. Before we move to Q&A session, we thought it's important to have a live demo and maybe to share with you some more details on the tools and the tool chain. What we will do now, we will hand over to Jill Bezard in France to conduct this live demo. Jill, feel free to take control for this session.
Thank you, Avner. I'm going to share my screen. This one. Okay, that's it. So I guess everybody can see my screen. So I'm Gilles Bézard. I'm France-based. I work for customer support, Europe, Middle East, Asia, and I'm also, well, I help a lot of customers for models, architecture, designing models, and even on the first steps when it comes to data and normalizing data and so on, the data sets. And of course, I'm better, well, of course, I can help creating TensorFlow models, but my point is when it comes to Akida models. So I will make 2 live demos just for you to realize that it's live and it's really happening the way you're going to see it. I'm going to take one what something showed, but I think it's important. It's edge learning, because it's just one-shot learning and it's learned on the device. There are very few of our competitors that can do that. And the second one is just to show you the power consumption real time, because we've got part of the API that can give you this information. So let me first begin with this slide that Todd showed us. I just want to give you a few more information about that. So you have to understand that you can install everything as a software to have the environment to develop. It's Python. You just have to ask Avner, and he will give you the link to download everything. It's not to download, in fact, it's to install, and then to get access to the documentation. And in these two arrows, the light gray one plus this blue purple, I don't know, dark gray, let's say here. If we focus on this one, on the first one here, almost everything is Python and TensorFlow or libraries, okay? And at least your model is TensorFlow. Here you create a model in TensorFlow, you train it under TensorFlow, this is TensorFlow, then you quantize it using one of our library, but you still have a TensorFlow model. You retrain it another time with fine-tuning or post-quantization training, depending the way you call it. And then you convert it. When it's converted, you can still run here and test for accuracy then. And then the second step, while all this is done on your side, you can ask for a device and then get the binary of the model and put it, map it, we say map it on the hardware. Okay, but you can do all this first step just asking Avner to provide you links and help and access to the documentation. And then for the second step, the one that was in the dark gray arrow on the previous slide. So you've got MetaTF, this Python libraries set, and then you've got 3 evaluation kits. The first one, so that this can be both through Avner or online, or I guess that Avner would like to help you to design and to choose the one which is the best. The easiest one and the cheapest one, it's the mini PCI board itself with the chip on it. Okay, you just have the PCI board plus the driver and you install it on a Linux machine. The second one is you buy a Raspberry Pi with the board installed and with several examples and an operating system installed and so on. It's one thing that I'm going to use for the demo I'm going to show you just right after that. Or if you prefer having a real kind of dev environment with a GUI, with a mouse and being able to develop and then after developing to map your model on the hardware, which is very comfortable, I have to admit, you can prefer a real x86 computer, okay? And then, so you can buy this, or that, okay? This is for the evaluation kits. And once again, it's an evaluation kit. It's not designed to be set in production. Once it comes to production, then we are selling 2 kind of things. The first one is the IP, of course, just like Robin told you. You get the IP that you integrate into the chip that you want to create, okay? Or the second one is if you've got a chip that would fit your needs, more or less, you can buy it from one of the resellers that bought the IPs already and that are creating some kind of general purpose chips that you can have through them then, okay? You can also have the one that we designed, which is called AKD 1000, if it fits your need, but it's a little bit big. I mean, we designed it to show all the things that could be done. So it has 80 NPUs, all interfaces with USB and all things that may be useless in your environment. So very often it's better to buy something small. Then this is the demo I'm going to show you here live. What I wanted for this demo, I talked with Avner, and it's the decision we made compared to all the demos you just saw that Rob and Todd were running. We wanted, Avner and I, to have something that where you realize that it's really live and it's embedded. So the set I prepared for this demo here that you're going to see, I took a Raspberry Pi. In it, I just plugged the board, which is going to compute everything. And you will see it because you will have the power consumption displayed live. I connect this to a camera, and you will see what the camera is going to see. And on this Raspberry Pi, it's the minimum that has been set. Okay, it's an operating system, but it's Ubuntu server, and on this machine, there is nothing connected except what I can show you here. Okay, I forgot the power supply, of course. You've got the camera, the board here, and an Ethernet Y connected here. And then here we also start a web server And I'm going to connect to this web server through my machine, the right one I'm using now, to show you what is doing on the chip. And everything you're going to see on the browser, it's something which is going to be run here on the Akida chip, okay? And then, how do you say, provided through the web server, which is also installed on the machine. That's why we needed a little bit more than just a MCU or something small. Okay, so this is the demo I'm going to show you now. Do not hesitate if you've got questions, or after you can say something if you need to. So I'm going to stop this presentation, switch to my device. So this is it. Okay, so here you can see that I'm on the local network, connected through this this IP address to the address of my Raspberry Pi, where I can run several demos. I'm going to begin with this one, just to have it real. You saw it for beer. It was for beer bottle. I'm going to do it with common life objects. So here it's taking a little bit of time, but it's just to start the web server. Okay, it's not Akida at all. The model is ready, and we just have to load the model. This happens. It's just web. The issue often is just the machine. Oh, again. Sorry about that. I'm going to start another one, but no. Okay, maybe if we can answer questions. I'll now switch to questions. I'm going to try to see what is happening here. I'm going to maybe start over the device.
Yes, Jill, I suggest that we'll move to Q&A when you're fixing this issue. And if you're ready, we will move on with the live demo. So let me start. I can see a few
Yes, I'm going to stop sharing my screen.
So although we did not conclude the demo yet, Gilles, thank you very much for the demonstration. If you are ready, let me know, and we can, of course, switch again to you. Let's go through some questions that we have. So again, you've seen this screen already. If you would like to submit a question, go to the Q&A session. Let me share a few questions that we have already. The first one is, do you have benchmark performance per watt for Halo 8 Edge AI processor? The answer is no, and it's not available. The benchmark that you saw is, as you could see, is with the NVIDIA Jetson and with the Coral chip. We don't have currently any comparison with the Halo technology. So this is the first question.
Okay, it's running now. I'm sorry.
Okay, so let me hand over again to you, Gilles. I will post share.
Okay. So you can see my screen, I hope. So this is what the camera is seeing. Okay, I move my hand in front of it. I'm going to show you this edge demo first, and then trying to show you a second one with face detection. So let us try to learn objects. So it's going to be real time. You're going to see everything. So I'm going to show an orange and make it big if I can. And so it's just, you see that I can learn it several times. I'm going to learn it only one time. Okay, that's it. And first, I'm sorry, but I forgot to do what you have to do at the beginning, which is to learn the background. It's better. So now this is the background, and this is an orange. I prefer it that way. So now let's learn another object. A book, for example. I've got one here. So this is the book. The orange is still learned, I guess. I'm going to learn a lollipop that I've got. Okay, so first it's detected as an orange. Well, it's not that bad. It looks like the shape, at least, is the shape of an orange. So let me learn it as a lollipop. Okay, so now it's recognized as an orange. Okay, it's sure it is. Okay, this is real time, so I can put back the object. I'm going to learn another one. I've got, what do I have? A tomato I've got for you. This is it, so I guess it's going to be an orange. Yes, sure. That's not that bad when you don't know what a tomato is. So this is a tomato now, okay, so we still have tomato. Sometimes it's recognized as an orange. I have the orange. Yes, I've got. Lollipop and the book, I think I will have no issues about that, okay? If I wouldn't be happy, we saw that for the tomato, it wasn't that good. Maybe it's the size, or we've got orange sometimes, yes. Okay, so we can make a second, I can learn a second time to have another tomato, because maybe the first, since you learn only once. Okay, maybe now it's better. Okay, no blinking about tomato. And it's only, you see one shot or two shot, or I did 2 or 3 for the tomatoes. Okay, now it's still an orange for this one. So this is the edge demo live, really. Okay, I'm going to see if it wants to switch to another one. So I'm going to stop this one. Oh, sorry, and I didn't display the power consumption. Let me do it with the detection demonstration. I can turn back to this one and have it with the power. I don't like demos that do not work. I'm sorry, I'm not that comfortable with it when it's come that way. Wow, again. Ah, no, okay. That is it. Did I? Oh, yes, okay, I started detection. Okay, so I'm moving into a detection demo, so you can see me. I'm in real time on both sides here, facing you on the Zoom session, and here facing the camera, which is connected to the P, which is just behind there. So I'm in person detection real time. I'm going to add the power for you to see the power consumption. Okay, so here it's real time, 80 milliwatts to have a person detection. And I can switch now, just for you. So it's a model which is already trained. I can switch to face detection. So if I'm facing the camera, I do not see if it's good here, but I guess it is. Okay, it's better even when it's my side, that my face is recognized and followed real time. Okay, so this is 6 frames per second, and well, it's going up to 94 milliwatts now. Okay. So that's it. Sorry for the first demo that wasn't that good. If you wish, I can turn back to the first one with the power consumption, which was around 70 milliwatts, if I remember well. Okay. Avner, you. Good. I'm going to stop sharing then.
Yes, thank you. Thank you very much.
And sorry for the first demo that failed. It's web. Yes, everybody have to understand that it's the web server that has a problem. It's not Akida. Akida was running behind the same way with no problem.
It's okay. I will not summarize yet. We do have a few questions. Jill, please stay with us. Some of them, I believe, will need your help here. And let me go to the next question. And it is, can one use Akida for the encoder, for an encoder-decoder type application rather than classification, i.e. artistic style transfer? Jill, is it something you can provide a feedback on?
It's difficult. It's difficult. You have to understand that in most cases, what is really easy for Akida to for a model to be mapped on Akida device is a kind of sequential model. So you can do something which is not, but it's a little bit tricky. You have to do kind of what I call surgery, trying to reconnect one layer to another one and so on. But the one, whether it's a dense model, kind of MLP, or if it's a convolutional one with a classical convolution and then classification at the end, this works perfectly. It's what is given in all the tutorials you could have. So what I suggest is maybe begin with this, just to be familiar with the way you can train a model and then you can convert it. See if you're happy, even if it's not the perfect architecture you would like for your model, and then we can help you designing another way and see how you can map it in several steps on the chip. But please begin with something which is, I don't know, easier even for you to train and to test as an accuracy when converted, and then try to see what it could give with another more tricky kind of model with recurrent networks and so on.
Okay, good, Jill. Thank you very much. Let's move to another question. You mentioned in your presentation running multiple neural networks in sequence, but does the Akida 1000 support multiple neural networks running simultaneously in the same device? I believe I can answer this question, and it's definitely yes. We've seen the demo, the first demo that Rob and Todd showed. We see a single device actually running 3 types of neural networks. One is for the visual wake, the second one is the keyword spotting, and the last one was the face recognition. So the answer is yes, definitely you can run several neural networks on the same device simultaneously. Let's move to the next question, and it's, can one extract the edge train model from the Akida-based platform in order to deploy it into another Akida-based platform? Is there a way to merge learn models? For example, if I have 2 robots who learn things individually, is there a way for them to later teach each other?
If the question is for me, I don't understand the question.
Let me make the question simple. Is there a way, assuming that you trained the Akida and you did edge learning, can you extract the data from the device itself and actually implement the same network which was learned in another Akida device? So assuming that you have many edge devices and you would like to share the same let's say experience with all the other devices.
Okay, so there are 2 questions in this question. The first one, if you want all your robots, for example, to share all their own experience into a new one, the answer would be no, because they would all have their own weights on this layer. So no. But if you want that something that has been learned on one robot could be transferred on another one, the answer is yes, because you would just have to get the layer and the weights that have been trained, in fact, and put them into another model. Yes. What you have to know when it comes to edge learning is that it's only the last layer which is learning that has its weights that can be changed. Okay. All the other layers have learned some kind of features that you're hoping to find again in the image that you are shown at the end. Okay, just like everybody is doing in edge learning. So once this layer has learned, of course, you can get the weights. But if another robot is learning at the same time something else, well, the weight would be different. So you cannot do something kind of merge with these two things, but you can, one that has been learned could be shared with others. So with this question, yes. And for the first question you answered, Avner, saying, yes, you saw in the core that was 3 models at a time. I'm afraid that I have to say we were switching from a model to another one very quickly, but Akida has just one output layer. So the output is unique. So if you want to learn to make inferences on several samples, you have to change the model. But you can upload and download different models. You can even, it's a way for me to understand a question, to answer a question that haven't been asked. You can even, if you've got a small IP, for example, let's say an 8 NPUs IP, but your model is 16 NPUs, its size, you can load the first half of your model, make inferences, keep the result, the vector that is have the result, in fact, on the chip, and then load the second part to have the full inferences. So we have designed the chip to be really fast when it comes to not only for inferences, what could be the target that everybody could see, but also our target was also to load and unload very quickly different models or different parts of the same model. We call them sequences.
Okay, Jill, thank you very much. I think we are running out of time, so I will go to the last question. We have a lot of questions here, but I will go to the last one. It's pretty much simple, I believe. Can the Akida device, the Akida 1000 device, operate as a host processor in an embedded edge product? To be more specific, can it run Linux, for example?
So yes and no. Can it be used as a processor? Yes, it is. It's an ARM M4, 32 bits. So yes, you can make it do a few things. Austin operating system, definitely not. It's too big. But what you could do, it's, I don't know, we're doing it. You can make it do pre-processing on the data, for example. This for sure. Okay, if you want something embedded that is going to make a small conversion or normalization on your data, the processor can do it for you, for sure. But hosting an operating system, no. When it comes to tiny, the idea is just maybe even having no operating system at all and just loading a binary of the model and then just making inferences on it.
Okay, thank you, Jill. Again, I think we are running out of time and people probably busy. So let me summarize. If there is any question, of course, I will put later on my details. Anyone can, ask questions. Feel free to contact me if there is any question you would like to ask. So let's summarize the webinar today. Neuromorphic computing is the next generation of AI. Processing the most relevant data smarter, faster, with ultra low power and most economical. This is the important thing. We aim to bring intelligence to the sensor in the device, the BrainChip Akida technology. MetaTF developing environment support native SSN, but also leverage standard CNN models design in TensorFlow. So again, Jill, thank you very much for participating in this event. We appreciate your participation. I would like to thank you all for taking the time and participating in this webinar. I hope it was useful for you. I will put down my details. You can see my contact details. Do not hesitate to contact me if you have any question or you would like further information. Feel free to do so. Again, thank you very much and have a Purim Sameach, everybody.
Thanks. Thanks, everybody.